Hello everyone, welcome to another class on the course on quantum theory of many-body systems in condensed matter here at the Institute of Physics at the University of São Paulo. My name is Luis Gregorio Dias, and in today's class we're going to go over the interacting electron gas and talk about the random phase approximation, or RPA for short. So we're going to start by defining this parameter Rs and see how the ground state energy of the electron gas behaves as a function of density and as a function of these Rs parameter as well. We're going to calculate the first order correction in the interaction for the ground state energy and see that it behaves as 1 over these Rs, and see also why when you talk about density, like the low density and the high density limits for the electron gas, that means more interacting or less interacting. We're going to see why is that. Then we're going to go over the second order correction and see that there's a divergency there. So there's a log-divergency and for second and higher orders, and we're going to discuss why this happens and then how we can get around it. And essentially we're going to do a re-summation of these higher order Feynman diagrams and get to the random phase approximation, or RPA, and see how these RPA actually in a sense changes the effective Coulomb potential between the electrons and makes it more short range, and that this making the Coulomb potential more short range actually helps to avoid this log divergency here. And that's essentially what happens in metals, this screening process that is described here mathematically by the RPA. Alright, so let's get right into it. Okay, so let's start by defining the so-called Rs parameter for the electron gas. And we do that by considering the so-called single electron volume, meaning that for a given density, what's the average volume that a single electron occupies. And we're thinking that since we have a 3D electron gas, we're considering this Rs as what is expressed in this cartoon here, that the volume will be a sphere with a radius which is proportional to the Bohr radius. And Rs is simply the factor of proportionality of the radius of the sphere and the Bohr radius, right? So this has no units, it's just Rs times the Bohr radius. So this volume would be then the volume of the sphere with a radius Rsab, 4/3 of pi Rsab to the cube. And for a given density, this is the inverse of the density, right? Since the density is the total number of electrons divided by the total volume, so this is 1 divided by the volume occupied by a single electron. So in other words, we're defining Rs in terms of the density, and here it's clear that the density goes as 1 over Rs cubed times this numerical factor here that will depend on the Bohr radius. So this is the important point. This is a parameter that we're defining in terms of the density. So the larger the density, smaller Rs, and vice versa. So the Bohr radius enters here this definition, and I'll just remind you that we can assign or attribute an energy scale related to the Bohr radius and the mass of the electron for a given electron, which is h bar squared divided by twice the mass of the electron times the square of the Bohr radius. This has dimensions of unit and is equal to 1 Rydberg, which is 13.6 electron volts. Precisely the energy for the ground state of the hydrogen atom that we studied in the elementary courses in quantum mechanics. And notice by the definition of the Bohr radius, this is equal to e squared over 4 pi epsilon times twice the Bohr radius, which is also 13.6 electron volts. And this, you can think of that as also has units of energy, kind of a potential energy with a distance of twice the Bohr radius. So these two quantities are equal to each other and equal to 13.6 electron volts. And if you remember our classes on the electron gas, and I'll try to put the link here, there we calculate the Fermi energy of the three-dimensional electron gas as a function of the density. And we have now the Fermi wave vector related to the density as such, right? Kf cube is 3 pi squared times the density. And this you can deduce by relating the volume of the Fermi sphere related to should be in proportion to the inverse of the volume in real space, and you get this this expression here. So since the Fermi energy increases with the density, and we also calculated how the total energy of the electron gas per particle is proportional to the Fermi energy, is 3/5, and we derived this as well. It means that this also increases with the density to the power 2/3, and the density to the power 2/3 will be the proportion to 1 over Rs squared, right? So it means that we can actually put a number here on this, the kinetic energy per particle for the electron gas in electron volts or in Rydbergs is going to be 2.21 divided by this Rs squared. Notice that this has no units, so the larger the Rs, the smaller the density, and vice versa, meaning that I can relate now the kinetic energy per particle of the electron gas to Rs, or if you could also relate it to the density, but here I'm choosing to put in this form. So this has no interactions at all, it's just a free electron gas. So this is the kinetic energy per particle. If you think this is what you should get if you have zero order in perturbation theory in the electron interaction, if you would calculate the energy of the ground state for an electron gas. So now let's take a look at the electron interactions, and let's try to get an estimate of the typical electron interaction strength in Rydbergs, say. So if the volume of a single electron is a sphere of radius RSAB, so you can think that a typical separation between two electrons would be twice that, 2 RSAB, and that give me a repulsion strength between these two electrons of E squared 4 pi epsilon 0 times this distance 2 RSAB, and then I can associate that with, say, the interaction energy for, say, every two particles, so that's divided by half of the number of electrons. So you can think of, well, a factor 2 here might cancel, well, but this would be of the order of the typical electron interaction strength per particle in the electron gas here. And notice that this will go with as 1 over Rs. This is 1 over Rs in Rydbergs, right? So this is 1 Rydberg, so 1 over Rs 13 times 13.6 electron volts. So notice that, well, if the density increases or Rs decreases, then the electron interaction will also increase, but the point is that the kinetic energy will increase even faster. The kinetic energy, remember, increases as Rs decreases by 1 over Rs squared. So the ratio between this and the kinetic energy terms, is actually proportional to Rs, linear with Rs, or goes with the cubic root of the density. And this, it might seem counterintuitive, since, okay, well, if the density is increasing, then my electrons are more packed together, so the distance between them will decrease. Well, yes, but if that's the case, the average kinetic energy will also increase even faster. So it means that for high densities, the kinetic energy wins, while for low density, the interaction energy wins. In other words, this ratio is linear with Rs. So the message here, and this is important to keep in mind, is that whenever I talk about the density of the electron gas, if I have high density, that means weakly interacting, while low density is a strongly interacting gas or strongly interacting electron system, right? So in other words, this Rs can be seen as a perturbation, the dimensionless parameter that will essentially count for the strength of the interactions in the system. So I can use that as a perturbative, if you want, factor to do a perturbative expansion in interactions at different orders of Rs, or at different orders of the interaction in the electron gas. So for high density, if I increase Rs, I'm going from increasing Rs means I'm going into the low density limit. I'm going from high density to low density this way. So I'm going from weakly interacting to a more strongly interacting. Okay, so now let's try to put some numbers on it and try to calculate at least the first order correction to the ground state energy of the electron gas in terms of this Rs. All right, so we are here at the blackboard, and for the electron gas, the ground state is, as we mentioned in a previous class, related to a filled Fermi surface in K space, so that all states here with a given K smaller than Kf in absolute value are filled. So, and for states with a K above Kf, they're empty, meaning that if I integrate in the entire volume of K space, the volume of this sphere would be this times this theta function, right? Kf minus absolute value of K. If this is Kf is larger than that, this is 1, then I can integrate. If this is larger than Kf, these states are empty and I have nothing there. And we use that to say calculate the free propagator for the electron gas before. We're going to see that later in this class. But this is the ground state. So if I apply with my non-interacting Hamiltonian to the ground state, I get the ground state energy, which we already noticed that it is proportional to 1 over Rs squared, the energy per particle in the non-interacting electron gas, 2.21 Rs squared in Rydberg's. And now we're ready to try to calculate the corrections due to interactions to this value. And this is going to be in an assignment, so let me essentially explain what the assignment is. essentially you're going to have to calculate the expected value of the ground state of the electron-electron operator, which is sometimes represented by this diagram, right? So we know that this is in Q space. So we already know the bare Coulomb potential, E squared over 4 pi epsilon 0, depends on the distance between the two electrons. And you Fourier transform that in class 13, that's the assignment there, to calculate this Fourier transform, and you get something that depends on 1 over Q squared. All right, so this is the one that we're going to use in this class. So this diagram has this form, and if you write them in terms of creation and destruction operators in K space, would look something like that. And just remember that here there's a sum over K1, K2, and Q. And just to tell you what those are, essentially you have to conserve momentum on each vertex, right? So if I assign a momentum Q to my interaction, and I choose it to be, say, going this way, right, this way, that would be a momentum Q here. Then I have to conserve momentum here and sum over these momenta, right? So I would have, say, a momentum K1 entering, K2 entering. So I'm destroying K1 at vertex 1, at this vertex 1 here. So I have to conserve momentum here, K1 going, Q out. So whatever's left here should be K1 minus Q. And now I have to pair the creation operators with the destruction operators for this vertex. Would be something like this. If I'm destroying my electron with momentum K1, so let's put it here. Oh, sorry, let's erase that. So that would be 1, K1. And I'm pairing this with this one, right? Remember how we build this interaction in second quantization. So this would be K1, K1 minus Q, while with this one I destroy at K2, right there, and create an electron with K2 plus Q. Right? This is the vertex, okay, for the electron-electron interaction. And now the assignment will be to calculate the expected value in terms of this, and I already tell you that there will be two terms by Wick's theorem, right? You have to do the pairings. One of them will give you a constant contribution, which will essentially be used to cancel out the positive charge that you have in the background for the electron gas, while the other one will be the actual contribution. And that's one of the assignments for this class. So if you do this calculation, the first order correction to the ground state energy, and you do this, that's in the assignment, the result would be something like that. It will be a negative sign, right, relative to the positive sign of the kinetic energy. So there will be a negative sign. And there's going to be this prefactor, and as we expected, this has to go with 1 over Rs. And this prefactor amounts to 0.916 Rydbergs. Okay, so we decreases with 1 over Rs as we expected. And if I now sum up these two contributions, the kinetic one and this first order correction, per particle, I get something like that, 2.21 over 1 over Rs squared minus 0.916 Rs. So as I expected, for small Rs, the kinetic energy will dominate. For larger RS, this will dominate, as this term will dominate. And if I plot this as a function of RS, I get something like that. A curve here for small RS, this of course will diverge, but because of this minus sign, there will be a minimum here, somewhere around there, somewhere around here, right? Let's see, maybe somewhere around here, and you can actually calculate this, the value of RS where the minimum occurs, and that's 4.83, around there. And you say, oh, all right, so this would be like, you know, the minimum for this, and you, if you calculate this in electron volts, and you plug this number back in here, and this is of course in Rydberg's, so you have to multiply by 13.6 to get the answer in electron volts, but you would get now what this energy is, and is about 1.3 electron volts, right? You can see it right from the plot here is about minus 0.1, and minus 0.1 times 13.6 is minus 1.3. All right, so is this a reasonable number for, say, metals? And in fact it is. Say for sodium you get minus 0.113, which is precisely the binding energy for sodium measured in experiments. And for other metals you have similar numbers, meaning you can see what's the RS corresponding to their binding energy, and they're, you know, around 5 here. So this means that this approximation is not too bad, right? This first order approximation is definitely better than what you get for just the kinetic energy only. Otherwise you wouldn't have this minimum here, wouldn't have this binding energy. So the question is if you can go further and try to calculate the second order contribution to the ground state energy. So given the relative success that we had in calculating the first order correction to the ground state energy, well, and notice that will be done in an assignment. I didn't mention that, but this is one of the assignments for this class. The question is, how about second order, right? Say like, well, let's try and do and calculate the contribution to the ground state energy from second order interaction. We can sum up the diagrams and to calculate this number, right? And I'll also put in the assignment that you should be able to see that this contribution actually diverges, and it diverges logarithmically. Essentially, you end up with integrals like this, was from 0 to infinity of dq over q, which gives you log of q, which for q equals 0, it diverges. So that's not good. Means that somehow our this second order contribution in a perturbation theory is actually exploding in our face. And let me try to give a hand-waving argument of why does that happen. So, and the hand-waving will come in the sense that I'm not going to go over the entire calculation, but I'll give you just a flavor of why does this happen. And the argument here I'm going to make is that this divergence comes essentially from diagrams with two or more interaction lines with the same momentum k. For instance, this diagram here. So this diagram here, let's erase this so that you can figure out together that these two lines have the same momentum. Okay, so a diagram like that, say I enter with k here in this dotted line, And this is one of the diagrams into the proper self-energy, right? This is a disconnected diagram, and there's this propagation line here. If I assign Q going that way to this interaction line, what I have here would be then K minus Q, and this line. Here, then I have one of these lines is entering this vertex, say this one, and the other one is leaving. So I assigned one actual number to, say, the leaving line. I assigned that an internal momentum P, meaning that if I'm entering with Q, leaving with P, I also have to enter with Q minus Q, right? So to conserve momentum at this vertex. And then I have to conserve momentum in this vertex here too. So I'm entering with Q, and I'm now exiting with Q minus Q, then I would have to have this interaction line exiting the vertex with momentum Q as well. So both interaction lines have the same Q. Now the diagram for this diagram then would be something like that, right? So it would have an integral of internal momenta, P, for instance, and Q as well. So and sum over frequencies as well. Not putting the sum over frequencies here, is all hand waving. But I'm very worried more about the momentum. Okay, so there's a Q here. So I'll have two interaction lines. So I'll get a VQ squared. And remember, VQ goes with 1 over Q squared. So VQ squared goes with 1 over Q fourth. And I have these other 3 propagation lines, right? One that doesn't depend on P, and the other 2 that do. So let's take a look at this integral and see why the fact that I have 1 over Q4 here is not good. So let's first look at this closed loop here, these 2 propagators, which is these contributions, the integral in P, right? This internal momentum here. So VQ squared will not enter this integral, but I'll have this G naught P minus Q times G naught times P. So once I do the integral in P, there will be something left as a function of Q. And I'm going to argue that the result of this integral will go as 1 over Q for small q. And why is that? Well, in the assignment, we're going to actually deal with this particular bubble diagram, and you're going to write that this can be written in this form, where you have these 2 theta functions here multiplied, and then the denominator you have these omegas minus pu minus q square, omega minus pu square. And the important point here is down here. So this would be something like pu square minus 2qp plus q squared. And you say, well, this is not really q squared because I have this contribution, which is linear in q, which will dominate over q squared for small p. So the overall counting of powers here for this integral as a function of q, there will be a factor of q squared too, but for small q, which is the ones that we are most worried about, right? So q going to 0, this will be the one that dominates q. All right. Okay. So then I go to the integral in q now. And so what do I have if I keep counting the powers? What I have is I have that 1 over q fourth coming from vq squared, and I have this other 1 over q here, and I have, of course, this factor of kf, k minus q, and the integral in q, of course, I can integrate the angles, and when I go down to integrating q, what I have is something like q squared dq, and here I have 1 over q fifth. So I end up, this integral will give me a contribution in k now, and remember, k is the variable that we are most concerned with, because that will give me the contribution for the self-energy in k. And this is what is going into the actual calculation, right? So I'll have to do an integral in k at the end of the day to get the energy contribution. And so if this gives me contribution of 1 over k cubed, there, when I do the integral in k and to calculate the contribution to the energy from this diagram, right? So I'll have an integral of angles, and then I'll have the radial integral, right? And this would be something like that, 0 to infinity or something, or to kf, right? It's going to be to kf, but something like there's a cutoff at kf because of these theta functions here. But then I'll get this k squared dk 1 over k cubed, then I'll get something like that. It might not be infinity, it might be kf, but it's already bad enough that I get the divergence for 0. So what I'm most worried about is this. So this is log k from 0 to kf, and that will give me a log divergence for small k, so for small energy. So that's an infrared, if you want, divergence. Let's put it even in infrared divergence. For q, so the divergence occurs for small q, for k. Right, so this diverges, and we, okay, now say, all right, let's put a cutoff here. Well, then it's arbitrary, right? So you need to take this limit to 0 at some point, and you recover your k. So if I put a cutoff here, a small k cutoff, means that I'm actually putting a large distance cutoff as well, right? So I have to regularize this and see what happens. And in fact, at the end of the day, the solution will enter not as a cutoff, but in noticing that maybe the interaction doesn't go as 1 over q squared as it's here, but with q squared plus something, that we are actually regularize these integrals. But this at this stage is a problem, and I have to see what I can do with that, and more importantly, where does the problem come from? And I'm going to argue that the problem comes from diagrams like this, where I have two lines with the same momentum, q, and those would give me these divergences. All right? So that's the point. So let's see how bad it is if I write out all diagrams that would contribute to the self-energy. All right, so in order to look for the most divergent diagrams, let's do this table that I took from the book by Roos and Flensburg, which is a very nice table actually. So here what do we have? I have the contribution to the self-energy from the different diagrams, and here I have the order of the diagram in terms of the number of interaction lines, right? One interaction, two interactions, so forth. And then the lines here, what I have is this delta is counting how many interaction lines with the same momentum that I have. So the diagram we just did was this one. Right, we figure out that this is Q and this is Q, so I have two interaction lines and two lines in total in the diagram. Now I'm going to argue that a diagram like this, actually, even though it has two interaction lines, the momentum for these lines are different. So let's take a look at this particular diagram here and see why this has only one line with the same momentum, so that the momentum of these two are different. Let's just take a quick look. So here we are. So this is the contribution to the self-energy, right? So we're calculating the self-energy with momentum k and omega, meaning that this line that goes into the self-energy has momentum k, and this one should have momentum k as well. All right, these are the external legs. So let's figure out what's going on here at this vertex, for instance. So I'm gonna assign, as usual, that there's a momentum q leaving here. Okay, so it means that the momentum of this other line in this diagram would be k minus q. That's the one. Okay, now then there's this, what's going on in this vertex, okay? In this vertex, I have this incoming line, which has an internal momentum. I'm going to call it P. And then I can, if I know this is Q, this is P, I can figure out what's the momentum on this line, right? The momentum on this line should be what? Should be, let's call it K2 or something like that. And K2 is such that it's leaving, so, and these two are entering the vertex, so this should be P minus Q. Okay. Now what's the momentum here? Let's call this Q1, for instance. Well, Q1 is such that, okay, let's make it leaving the vertex, right? Could be entering, doesn't matter. I'll just get a minus sign here. Would be such that there is this k minus q entering, and q and p are leaving. So actually, let me do it like this. Q plus are leaving, it should be equal to what's going in, which is k minus q. So Q1 would definitely not be equal to Q, but would be K minus P plus Q. All right? So, which makes sense, since if I add K1 with K2, I should get K, and that's exactly what's going on. So this is correct. So I would get a diagram here with not two lines of Q, but one with Q and the other one with, say, K minus P minus Q. All right? And so this would be K squared, and this one would be 1, well, there would be, right, so if I take this square, would have K minus P squared minus 2K minus P at most, depending on the angle, but it's the angle between these vectors. What if the angle is 0, would be something like that, right? And at most, for small q, this term would dominate, not this one, which is not as bad as this one. So this would be like K minus P times Q. So instead of 1 over q to the fourth, I have something like 1 over q to the cube for small q. For small q. So that's not too bad. It's not k to the fourth. All right? So let's go back to that table. So we're back to the table. And now we figure out that the divergent diagrams are these ones where I have the same number of interaction lines in that diagram as they have the same number of momentum. So I'm talking about these diagrams here in the diagonal, where delta is equal to n. So it's a diagram with order n, where all interaction lines have the same momentum. So these are the worst of the worst, right? And notice that they have the same structure. They have, these repeating bubbles appearing connected by these wiggly lines. And that's, of course, that's what you should have, so that you have Q, and then Q above the bubble, right? And then Q above the bubble, and so on. So all these lines have the same momentum Q, and these are the diagrams that I should be worried about because they are the divergent diagrams. So what's the idea here? The idea here is to construct your self-energy by summing up all these diagrams first and disregard the other ones. So that's the approximation that we're going to do, and sometimes called the RPA approximation. So in doing that, I'm going to write these diagrams in such a way that I'm actually going to renormalize the interaction lines and make these diagrams, at least the sum of them, not too divergent, right? So essentially, I'm, in a sense, trying to cancel summing up these diagrams, because notice that they have a different number of fermionic loops here, right? So this one has 0 loops, so there's a sign of plus. This one has 1 loop, a sign of -1, and here I have 2 loops, a sign of +1. So they have these alternating signs, and by adding them up, hopefully there'll be some cancellation of infinities going on here, so to speak, so that the sum, even though each diagram in particular will create a divergency, maybe the sum of all of them will not. And that's the idea behind the approximation. So this would be the random phase approximation for the self-energy, that I then add all these diagrams here with a momentum k omega, frequency omega. I took this drawing from Bruce and Flamber's book, so the notation is a bit different, but you can think of these k's as momentum, right? So I'm adding then all these diagrams. They all have all the interacting lines have the same momentum, right? Q, 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 and they all have these structures in terms of these bubbles, and we're gonna worry about them in a minute. But first, let me notice that I can decompose this into this form. There's always this propagating line here with momentum k minus q in all of them. And that's, well, because, I have to conserve momentum in these two vertices. And if all the interacting lines have the same momentum, the momentum here will always be k minus q. So this would be like this free propagator with momentum k minus q times this series of diagrams. And I'm going to call this series with alternating number of bubble diagrams of, I have 0 here, 1, 2, 3, so the overall signs of these will be alternating as well. And I'm going to call this the RPA potential. Remember, there's this minus I in terms of when you discuss a diagram like that, like this is minus I times V of Q. And I'm going to represent this sum with this thick wiggly line, and that's my RPA potential. So at the end of the day, this will be my self-energy, and this will be my my approximation, my random phase approximation for the self-energy. So one question that often comes about when I talk about RPA is, why do I call it a random phase? What is the random here? Well, there's nothing random in terms of these diagrams, right? I can evaluate them in a very precise way if I know the propagators. And the name random phase approximation actually, it comes from historical reasons, and it persists to this day. And the idea, I mean, you can see in these early papers there's a series of papers by David Bohm and David Pines where they introduce the approximation. And in a very crude terms, what the random phase comes in is that they write the Coulomb interactions in the free basis, in the non-interacting basis in terms of plane waves. And so you have these exponentials, right? E to the k times the position, with different k's for, so you need two of these to do an interaction line. So that's when you write the Coulomb potential in that basis. And it turns out that when they have the other diagrams in that table with many interaction lines, but the momentums are all mixed up, they're not the same momenta, it's essentially they argue that is equivalent as randomizing the phase of the plane wave. And when you randomize, when you sum over all the internal momentum there, because of this quote-unquote random phase, they'll cancel out, and that's the approximation, that they only keep the terms where the interactions they come with the same momentum. But it would be nice to, if you could take a look at this. This paper is actually this one is a third on a series of papers where they talk about the collective description of the electron interaction in the degenerate electron gas. That's the system we're talking here. And one curiosity and a historical information, especially for the Brazilian students watching, is that this paper is from 1953. And at that time, David Bohm was here in Brazil. He was here, actually, he was a professor at the University of São Paulo. And he stayed here for about 4 years, from 51 to 55, early 55. And he signed his papers from the University of São Paulo. It was a time where he was very productive. And he came here, he left his position at Princeton due to political reasons, right? So the early 50s was at the time where you have that Committee on Un-American Activities led by Senator McCarthy, and David Bohm was, a little bit worried about that. So he came to Brazil and, helped to shape a little bit the School of Philosophy here, that was before the Institute of Physics. So that's a interesting historical note that especially the Brazilian students should be aware of. So let's keep going and see what this RPA approximation takes us. Okay, so now let's take a look at these diagrams, these loop diagrams. And I'm going to define this quantity I times pi 0 of q and omega q, which is essentially the quantity defined by these diagrams. Sometimes these are called the polarizability, and is very much related to the density-density correlation function that we calculated in the class on linear response for, say, the linear response, the dielectric response of the electron gas. Sometimes they're just called the bubble diagrams, sometimes the inserted polarization, but they're different names, but this is the quantity. So I can evaluate these diagrams, right? So these are free propagators, so they have momentums and frequencies associated with them, and this would be one of them would be Q, and the other one would be Q plus Q or Q minus Q, depending on which you are evaluating. But at the end of the day, this would be something like that. If you would take the propagators here, Ig for each, there's a -1 coming from the fact that this is a fermionic loop. You would get this pi 0 equals of Q and omega Q. There's be a sum over spins that will give a factor of 2 here if the electron gas is not spin polarized, of course. Then there's this integral in P and this integral in omega P, which are the internal variables here. So that's this diagram. And as I mentioned before in the assignment, given the free propagator that we calculated in the previous class, in the assignment you're going to write this as in this form, right? You're going to show that it can be written in this form, which is the one that we referred to earlier. So these are the bubble diagrams, and now this is what enters in the self energy in the RPA approximation. So let's see if we can write that in terms of an effective potential, the RPA potential. All right, so we define then the RPA potential as this sum. So this is defined as this wiggly line. There's this -I here for the propagator. And it is then the regular potential, the Coulomb unscreened potential, the bare Coulomb potential, plus the first contribution would be the second order, right? To Coulomb lines connecting one bubble diagram, then two bubble diagrams connected by interaction lines, so on and so forth. Now notice that here, since this structure repeats itself, right? So it's always a bubble diagram with more lines and more bubbles and so on. I can factor out one interaction line, one bubble diagram, and times this wiggly line here, right? Essentially, I'm taking a cut here, right? And then here, and this structure would follow precisely this: a wiggly line, and a bubble, then another wiggly line, and two bubbles connected by two wiggly lines, and so on and so forth. And what enters here is precisely the same definition as the RPA. So it's kind of a Dyson's equations for the RPA potential, which we can write in this form here, right? RPA equals this bare Coulomb potential plus this, which is the kernel, plus the RPA itself. And here in frequency and momentum domain, these are just multiplications. So I can write a kind of a Dyson's equations for this RPA, and if I know how to calculate these bubble diagrams, which I do, and if I know which are the potentials, which I also know, right? I can in principle calculate. I know how to Fourier transform. This would be 1/q squared. I can calculate this, right? I can have a closed form for RPA in different orders, and I can actually expand this in different orders of this polarization diagrams. Okay. So that's one way we can calculate the RPA potential. So let's see how we can do that in practice. And And the question is whether this help us or not with those log divergences that we encountered earlier on. Okay, a few comments now on these results. First one is that, as I mentioned, we can formally solve the Dyson's equations for the RPA potential as this. So if since there's an algebraic equation in momentum and frequency space, I can essentially solve it by doing this form. It would be the bare Coulomb potential divided by 1 minus the polarizability times the Coulomb potential itself. So diagrammatic would be something like that. This thick wiggly line equals the Coulomb line, 1 minus this times the bubble diagram, which is represented this, which in principle we can calculate. And I'm gonna at least try to convince you that this would give me the end result of this term here would make the Coulomb interaction more short range rather than long range. Okay. The question is whether that solve our log divergence that we had in the calculation of the ground state energy. And the answer is yes. In fact, I'm not going to do the calculation here, but this extra terms making the Coulomb interaction it essentially will give you a cutoff. At the end of the day, that's what's going to happen, and we're going to discuss that in a minute. But it will not explode for Q going to 0. It will give you something else, which is sometimes in the Thomas-Fermi approximation is also a cutoff momentum there. So and that regularizes the second order contribution from the interacting part. The second order contribution now, instead of exploding, actually will give you something that goes with log of Rs. Remember the first two terms, one was the kinetic energy goes as 1 over Rs squared. The first order goes as with a minus sign, 1 over Rs. And now there is this constant term actually, plus this term that goes with log Rs. So it does not explode, but still increases with Rs, and this already in units of Rydberg. And superior orders will be something like Rs times log of Rs, so now things seems to be well behaved. And if you want to see the full calculation, just look at Fetter and Valekan, section 12, they do that. It's a very instructive to look. Now, going back to this issue of the cutoff, and I'm going to argue and try to do some back of the envelope calculations here, that if I look at this at the limit of zero frequency and small q, this actually has this form of something. Instead of just 1 over q squared, it will be 1 over q squared plus this constant, which sometimes is called the Thomas-Fermi momentum. But this, as I mentioned, gives you a cutoff in momentum space, so that when q goes to 0, this does not go to infinity, but goes to a constant, 4 pi e squared times this Fermi momentum squared. So that regularizes those contributions coming from second order processes, and then everything, you don't have any more log divergences anymore. The limit for q going to 0 is finite. And in fact, you can relate this QTF with Rs and the Fermi wave vector as this. So as Rs increases and you go into the lower density, this one also increases. So that's good. Means that even for moderate values of Rs, this should also work and regularize your expansion there. Another point is, as I mentioned, the fact that you have this finite cutoff in momentum also gives you a short-range nature to the Coulomb potential, right? So this is sometimes called screening. And in fact, if you, and I think that was one of the assignments in assignment 13, if I remember, where you should calculate the Fourier transform of something like that. Not the bare Coulomb potential, but one with this exponential reduction, right? Which is like a Yukawa potential. And that will give you QTF square here, right? So this is like an effective range for your Coulomb potential. Is not long range anymore, but has this shorter range form. Okay, so let's just do a quick calculation and see where does this expression come from. So here we are. So let's try to give an idea of why we get that cutoff. So first, let's just do a quick calculation here by substituting VQ here, and I should get something like that for RPA, okay? Q, and let's take that to, all right, omega Q. This should be then E square over epsilon 0. That would be a 1 over Q squared here, right? And I'm already putting here, minus Q squared pi, and that's E squared epsilon here, Q squared. So this one cancels out. This should be just E squared over epsilon 0 plus Q squared minus this pi of Q omega Q times a constant. All right, so that's what I'm going to call this is minus. I'm going to call this minus Q Fermi, Q Thomas-Fermi square for at omega 0. Right, so we already know where does this thing come from. Like if I want to, this is going to be negative actually, right? So this is minus something positive, and that's my Thomas-Fermi momentum. Okay, so let's do a quick evaluation of this guy for omega Q around 0. All right. Then who are these energies here? So I have EP equals HP squared over 2m. And what's EP plus Q? That's H P plus Q squared, which is HP squared over 2m. Let's write this as this. Equals HPU plus HQ plus what? H bar 2m times P scalar of Q times 2, right? So yeah, P scalar, which is, so what I want is this EP minus EP plus Q is approximate, well, there's going to be this minus EQ, but I'm taking the limit to equal 0. This is not going to be important. But the point is that this should be of the order minus 2 PQ over M. Okay, that's the important, which is if I take the cosine, say, between P and P minus Q to be his angle to be theta. This is, I can write this for P going to 0, this would be something like minus PQ P, oh sorry, something like that, okay, with this m here. Okay, now let's look at these theta functions here and this minus sign. Let's go down a little bit, and I'm going to write the two theta functions. So at first I have this one, kf minus p, and another one which is p plus q minus kf. And the other one I have the inverse, right? P minus kf, theta of kf minus p plus q. Okay. So let me look at these two. So in the first one, let me call this 1 and this 2. So in the first one, I have a situation like that. So the absolute value of P has to be smaller than Kf, right? So if my sphere, my Fermi sphere is here, right? So this is Kf. So what I have is Kf has to be larger than absolute value of P. So if I draw it like this, P has to be a little bit smaller than Kf. It can be close, but it has to be a little bit smaller. While P plus Q has to be larger, right? So I would have something like that. P plus Q, larger than Kf. So the momentum Q would be this, right? This is Q, so that this angle theta, so in this case, I could try to approximate if P is approximate, is almost Kf, then this should have K with a cosine of theta, right? Where theta should run from 0 and pi over 2. So that this would be, so this theta here would be larger than 0 but smaller than pi over 2. Okay? All right. So, I mean, the angles would have something like theta with cosine of theta, where theta goes from 0 plus or between 0 and pi over 2. Now let's go to the other one. The other one would be something like that. This is Kf again. Now P is a little bit larger than Kf. Okay? So I have something like this. This is P. And P plus Q in absolute value is a little bit smaller than KF. All right, so now my vector Q is here, meaning that the angle is smaller than well, if I measure the angle right like this, I don't have to measure the angle like this, is larger than pi over 2 and smaller than pi. So in this second case I would get something like that, even though P might be closer to KF. This would be minus Q cosine of theta, because theta, cosine of theta now is negative, right? Because theta has to be between pi over 2 and pi. So Q cosine theta is negative. That's the point. That means that if I go back to the integral here, right, I would keep these angles in a sense opposite. So I would both of them would get the same sign overall, since the sign coming from the integrand has to be different. Okay. So let's go back to the integral and see what you get. So I have this, so I know that the angles, if I define the angle theta in the two terms, would be different. So I can just define this angle here to be, I don't know, theta minus pi over 2 or something, and I then can integrate both of them in the same variable here. Now that integral will have, well, apart from the angular part and whatnot, there's the integral in cosine of theta still be there. So I can hand-wavingly say something like this, so that my integral of my pi 0 would be something like an integral in 0 to in this region, right? So I in a region, in a small region where P is of the order of K of Q, because it's the intersection between these two regions, P around KF, but P of the order of Q, but there will be a P square, so it's definitely not over the entire volume. I have this constraint here, P dP, and there's this integral in cosine of theta here, cosine of theta, and in the denominator, so this would be the same sign, so I can add them up. In the denominator, there will be something which will be proportional to cosine of theta, right, divided by m. So here would be something like PQ cosine of theta. There will be an m multiplying, but this is the integral in cosine of theta, so I can do. And I'm going to argue that, okay, so there's a p square here, there's a p cube up there, there's p is going to be close to q, so I would say that this p square cancel this p over p times q, and I'll have something where p is about kf. So hand-wavingly, this would give me this m. There will be a kf, and perhaps some factor of pi. It's going to be pi square actually, but definitely it would be something like of the order of m, because there's an m in here, and kf, since everything is happening around kf. So that is essentially my pi 0. And if I go back into my integral there, so kf square would be k Thomas-Fermi square would be pi 0, yeah, there's a sign of minus here, right, because of the loop, this overall sign here, factor of 2 and so on. So, but it would be pi 0 times e squared over, which would be something like mkf e squared over pi square e0. So that would be my Thomas-Fermi cutoff, Thomas-Fermi momentum. Okay. Yeah, actually there's it's not exactly this, but has roughly, okay? Anyway, the point is that this pi would be of order kf, and so will kf squared. So you can actually notice that K Thomas-Fermi would be of the order of the Fermi wavelength. Okay. Yeah, there's this mass here. I might get another KF. There would be something like, at the end of the day, since there's the mass, there's E, there's this mass, E squared, or E0. Actually, Thomas-Fermi would be of the order of KF at the end of the day, right? Because this mass here. All right, so essentially that's the idea, that I would get this cutoff when I calculate these diagrams, these bubble diagrams here, and this would be a cutoff in momentum, which might be of the order of the Fermi wavelength. All right, so let's go back to the slide to wrap this up. So just to wrap this up, you can actually do the calculation correctly, and not the hand waving way that I did, and you can, Finifetter-Velac is also done, and you get to this result, which QTF is proportional to KF, and there is this square root of 0.66 times RS, so it does depend on RS. But anyway, that was the message here, and this is the idea for RPA and how you regularize these divergences in the electron gas by resumming the Feynman diagrams. All right, see you next class.